Um, Another type of force problem we can see, it's very similar to just having one force acting on it, but what happens if we have more forces acting on it? How can we interpret that? Let's pretend for a second we have like a countertop. And on this countertop, oh no, it's at a slant. I don't want that. Undo. It's because I'm at a slant. It's because I keep lifting the pen up. Not good enough. It's flat. It's a flat countertop. We have a block or something on it. Okay. Let's say this block has a mass of 8 kilograms. If we have two forces acting on this block, one to the right at, let's just make a number, 17 newtons. And let's say that the block begins to accelerate to the right at a value of, oh, I don't know, 0.4 meters per second squared. What is the value of this mystery force on the backside? There has to be a mystery force on the backside here, because if you tried to find the acceleration by taking acceleration equals force divided by the mass, if you did 17 divided by 8, you get 2.12 as the acceleration. And the acceleration I gave you is 0.4. So there has to be some mystery force here. To find this mystery force, we need to set up the F net equals ma. Something that I also like to do, and we'll talk about this more in class, how to draw them, is to create a free body diagram. We see here I've kind of created this diagram with the block just sitting there. A better way to draw this block scenario is to redraw the block as a dot. This is our free body diagram. And then draw the forces coming off of that dot. Okay? We know this force going to the right is 17 newtons, so we can draw an arrow and place the 17 there. We also know that the acceleration is going to the right. So when we draw our vector going to the left for that unknown mystery force, we know it can't be as big or larger than 17 newtons. Because if it was, the block wouldn't be accelerating to the right, it'd be accelerating to the left. So when we draw the second force, it's often nice to keep in mind the relative size of the forces, and this one is smaller. We don't know what it is. I'll call it F2. Let's give it a number, or a value, like some lettering. But we don't know what it is, but it has to be smaller. And oftentimes, a lot of people like to look for size conventions, or just, are you giving a general idea of what's going on in this problem? Okay. Now that we have our free body diagram, we can write out our F equals ma, depending on how you like to write it. Sum of the forces, or F net, or just good old F, is going to equal the mass times the acceleration. Okay, so that's the equation we're using. Same old equation, but just new way of setting it up. In order to do this, we need to choose a positive or negative direction. It doesn't matter what you pick, but we need to choose it. So if we kind of look back up at our pictures, let's choose the right as being positive. When we choose the right as being positive, not only do we set the 17 as being positive, but we also set the acceleration as being positive, because it is going to the right as well. This second force in green that we don't know, it's a negative value. Okay? So whenever we list out our F equals ma, the way we'll do this is we'll place all the forces there and try to add them together. So for our net force, we have 17 newtons. It's positive because that value is positive, going to the right. And then since this F2 is going to the left, we subtract it, minus F2. We don't know what F2 is, but we know it's going to the left. We know it's negative. When you're adding a negative number, that's the same as subtraction. And this equals ma. Our mass in this problem was 8 kilograms. Our acceleration in this problem was a positive, because it is being pulled to the right, 0.4 meters per second squared. Okay. If we go and work this out a little bit, we can see that 17 minus F2 equals 3.2. And at this point, everything is technically in newtons. The 17 is in newtons from above. F2 is a force. It is in newtons. And kilograms times meters per second squared from our mass times acceleration is also in newtons. And since everything is going to be in newtons, we're allowed to add together. Remember, you can only add things together if they have the same units. So if we now can add things together, we can kind of move some stuff around here. What we're going to do here is we are going to subtract 3.2 newtons from each side. So it's going to go over here. And we're actually going to add F2 to each side. So it's going to go over here. So if we rewrite this, what we're going to have is 17 minus 3.2, all of that is newtons, equals F2. And 17 minus 3.2, you don't need a calculator for that, but if you wanted to, you could. 13.8 newtons. That's how much force is pulling to the left on this block. So this up here is actually 13.8 newtons. That was our mystery unknown force. And the way we did that is we drew a lovely picture, chose a direction, set up F equals ma with both of our forces equals a mass times an acceleration. We made sure our acceleration had the correct unit, or the correct sign rather, because it is being pulled to the right, and we called that positive. And then we just crushed through the math until we get our final answer here of 13.8 newtons pulling back on the block to slow it down. And that's how we can do a slightly more complicated F equals ma problem. We're done with that.